All right. First of all, I want to thank Carlos for inviting me here today to give a talk. I think the main reason I'm here is that I'm 3 doors down from his office in the University of Washington. My day job is I actually am a computer architect, not a machine learning expert, so it's a bit of a different talk. I want to warn you that I woke up yesterday very far away from here, so there's going to be a bit of randomization in my talk as a consequence, but I hope to not to make it too bad for you. So let me begin by asking a rhetorical question, which is why is a computer architect here at ostensibly a workshop based on machine learning and GraphLab? And what computer architects do, the sort of bread and butter, is we try and optimize the processing and the memory and the network connectivity between those devices such that they work well for operating systems and applications. And one of the things, or one of the themes in my talk, is that the important technology trends that we as an industry have always expected to keep going have changed quite dramatically. So all of you know about multi-core. All of you have probably heard about Moore's Law. But how many of you, raise your hand if you heard about Dennard scaling? One person, right? Dennard scaling is why my profession inflicted multi-core on you guys, right? Most of you would be much happier to program single-threaded cores that were much faster. But Dennard scaling is about how you can, or as we have now, cannot scale down the power consumption as you increase processor generations. So as a consequence, we gave you all multi-core and we hoped you'd buy it. So one of the other consequences is the major technology trends and the ratios between various features like processor speed and network speed are quite different today, and that allows you to build some interesting software. So in fact, for the last 6 years, I haven't really done hardware research anymore. I've been doing runtime systems and software development. So what I've been doing for the last 3 years is focusing on this system that we call Grappa. And what Grappa is, it's a runtime system for the efficient scale-out execution of irregular applications. So what is an irregular application? Graph analysis is an irregular application. As I mentioned, it's a runtime system, so you can actually use it as a foundation for many different platforms that you might build on top of it. For example, you could imagine porting GraphLab to it or Hadoop-style MapReduce applications to it. Just as a teaser, as a way to sort of keep you in the room and hope you'll pay attention, here's the performance of Grappa. So what you see are three systems here. One is Grappa, one is GraphLab, one is a Cray XMT supercomputer. And what we're able to do with just a piece of software is take a commodity cluster and make it faster than one of the most expensive machines you can purchase today. And so that's pretty interesting to us. What's also interesting, hopefully to you guys, is it's not that hard to program. So we'll go through this in a bit more detail, but this is breadth-first search. And it's coded in a way, which we'll see in a second, I hope, that you would like to code breadth-first search. It's a bunch of parallel loops. All right, so Grappa gives you high performance and reasonably easy programming model to learn and use. Okay, so what are sort of the opportunities and challenges that happen in technology, or are happening in technology, and that basically started around 2005 with the end of Dennard scaling, but the continuation of Moore's Law? This is my lovely daughter, by the way. This is what I spend the other half of my life doing, is raising her. So Moore's Law. Moore's Law we all know about. We probably don't necessarily know exactly how it was codified 40 years ago by Moore. But what it has given us today is ever more transistors that are running ever faster. And this is actually continuing. So even though single-threaded performance, or the performance of a single core, has bottomed out, Moore's Law itself, which is about the cost per transistor, is continuing at least for another decade. After that, my community is really not that sure what happens. People have been predicting the end of Moore's Law about every 5 years, and in fact, I think the rate at which people predict the end of Moore's Law is doubling every year. But pretty much, I think you should just count on it continuing. But all is not well with technology is scaling, all right? So processors, as I mentioned, are not getting any faster. What is interesting, I think, is that bandwidth is continuing to increase. So just the raw technology gives us ever faster transistors and ever faster communication speeds. And memory is continuing to get denser. And so what's interesting for me as an architect and a software developer is that the ratio between these factors, in other words, the ratio of bandwidth to compute speed is changing exponentially as technology marches on, where in the past it has continued on forever. Or, sorry, in the past it's remained relatively constant. And so the fact that these are changing allows you to write some pretty different types of software. Okay, kind of another opportunity, of course, is that we have a commoditization of operating systems and tools, right? You would like to have all your analysis and all of your machine room basically full of commodity hardware and commodity operating systems, because you can hire people that understand how to manage that, and when it dies, you can go out and cheaply buy some more of it, right? So nobody likes the kind of one-off strange boxes you sometimes have to purchase to process data in this space. The second challenge is something we're all aware about, and the first two talks touched on this, which is that it's difficult to take graph data and partition it uniformly across a cluster. And so this creates an excessive amount of communication, it creates load imbalance, lots of challenges when it comes to writing algorithms in this space. Another challenge, actually, is if you look at commodity hardware, it's really tuned for, commodity networking hardware. It is really tuned for sending large quantities of data around. So most of you probably purchase commodity hardware based on the stated bandwidth that you purchase. So for example, 10G Ethernet or 32G InfiniBand. Under the hood, there's another number you might want to pay attention to, which is the packet injection rate. So for example, 32G InfiniBand, sort of the latest cards, actually have only about 10 million packets per second. So what that means is that in order to get that full bandwidth, and not just a small fraction of it, you need to send relatively large packets of data around your network. Right? So in order to do that, if you think about it, if you want to take a fine-grained parallel program and you want to run it on a large cluster of machines where the messages that are being transmitted around are only 64 bytes or 8 bytes, you're not going to get the bandwidth you purchased. You're going to get about 5% of it because the injection rate is much smaller. Right? So this is a major challenge you have to overcome, and you overcome it by blocking and aggregating data together, as does GraphLab as well. The third challenge is you want to be able to write software in a programming language that you understand. You don't want to learn some specific, domain-specific language. This is my former PhD student at a Christmas party. We gave him this sign as he was about to graduate. So you want to be able to use commodity languages, commodity tools, and you want to be able to use them easily. All right, so now I'll introduce Grappa. So Grappa is as I mentioned in my second slide, it's a runtime system. It's kind of a foundational layer at which you build higher level applications and toolkits on top of. So all talks have to include a stack like this. At the bottom we have our processors and our memory and our networking, sort of our raw physical hardware resources. Above that, we're going to allow Linux to manage the processors and the memory. And we're going to layer on top of that sort of the core Grappa system, which provides sort of three basic mechanisms. So it provides a tasking layer for managing millions of fine-grained tasks across a large cluster. It provides a PGAS-style global addressing system, so you can address memory remotely on any node. And it provides a messaging system that allows you to efficiently communicate between nodes in that cluster. And that messaging system is going to just use off-the-shelf MPI to talk in user space to the networking hardware. What's important to, on top of that, we're actually going to build a collection of data structures and algorithms. So these are things like arrays, queues, graphs, and so on and so forth. And algorithms are things like breadth first search, connected components, stochastic gradient descent, so on and so forth. So a collection of Grappa nodes, so each of those that I've shown, that was a physical node, and then we're going to be able to scale out to a large cluster, and a single Grappa system looks like many instances of a Grappa system can combine together to, again, give you the same programming model. So you have a single PGAS shared address space that is all connecting between them. So what you can do is you can imagine writing your algorithms on your one node system to debug them, and then you just scale out, and you go and you order 128 nodes, for example, and scale out to larger data and more computational bandwidth. Okay, so what I'm going to go through now is I'm going to go through each of these three pieces, the tasking, the global memory system, and the messaging, and sort of show you a little bit in more depth how each of them works. Okay, so the first is the tasking layer. So as I mentioned, Grappa gives you hundreds of thousands, millions of threads across a large cluster. And we actually use this throughout the system to tolerate latency. So we need to have many, many thousands of threads per core active at the same time because the latency of execution of any particular thread is going to be actually quite high, but the bandwidth of execution of a single core will be quite high as well as a consequence. So it turns out that systems, hardware systems have been built to do this in the past. So Terra, which is a supercomputing company that got started in Seattle that ultimately bought a company called Cray and then adopted its name. They got its start by actually building a machine called the MTA. And the MTA was an interesting machine in that it had hardware thread contexts. So every time you would issue a request to shared memory, the processor itself would context switch and go off and execute another thread. And so in this way, each individual thread never actually observed the latency to memory being high because the processor itself kept going busy. So they never actually stalled. Turns out you can play the same trick on commodity hardware. So you can write a very fast scheduling algorithm, a scheduling mechanism, and you can stack thousands and thousands of threads on a commodity cluster, or sorry, on a commodity multi-core chip, and you can tolerate an arbitrary amount of latency as a consequence. So Grappa plays this trick. There are two types of threads in Grappa and a couple different thread priorities. It's kept very simple. So there's user threads that you as a software developer write, and there's system threads that we use to manage the movement of data and so on and so forth. Tasks can migrate to tolerate load imbalance. They can also be bound to particular cores if you believe there's a high amount of locality on that core. Each core in the Grappa system manages several thousand threads, as I mentioned. The number of active threads at any particular time is bounded, which has a little bit of wrinkle to the programming model. And tasks are assigned to workers as needed to tolerate latency. So what the system does is it's observing the amount of time that a processor is stalling due to remote memory accesses. And if it's too high, it goes off to the task pool, acquires some more tasks, starts up some more threads, and tolerates that latency. So the task pool is expected to have millions, if not billions, of tasks, and the worker pool is finite and small. The other trick that Grappa plays is throughout its runtime system, it trades off latency for bandwidth. So whenever there's a high latency operation, we're going to try and keep the actual system executing at peak bandwidth, whether that's the processor or the network, by trading off the cost of that individual transmission or execution for the in aggregate way at which we can execute or send. So going back a few slides, I mentioned that networks have a high bisection bandwidth, but a low packet injection rate. So what we're going to do is we're going to take multiple messages that are going to a remote node, and we're going to combine those together, aggregate them together into one larger packet. And then when we have enough of them, then we will send that packet on the actual physical wire. So how well does it work? Well, works pretty well. So what we're able to do is up the packet injection rate on commodity hardware by about a factor of 20, just using software in this way. And so we can get some pretty respectable GUPS numbers. On this chart on the right, GUPS is a random access benchmark where you have essentially you're sending a request to update an array anywhere in the network. So the x-axis is nodes, the y-axis is GUPS. And what you can see is that with just a handful of nodes, you can achieve a very respectable GUPS number comparable to thousands of nodes of a supercomputer. Some implementation notes, if you're curious, you can ask me later about all the details of this, is that you have to aggregate these requests hierarchically, so we gather up requests across all the cores in a system, and then we dispatch that large request to a remote node, and then it's deaggregated across all the cores in a system. And there's also a lot of careful scheduling and prefetching going on in the hardware to make this efficient. Okay, the final point is, you don't need a domain-specific language to write highly parallel code. C++11, as kind of wonky as it is in some places, has introduced Lambda functions and other interesting features. And so it makes it possible to do what you used to have to do in a DSL in sort of straight off-the-shelf C++. So this is a parallel loop where we're just pushing things onto a queue. I have a more interesting example later. And through sort of careful construction of the data structures and the PGAS style addressing, this parallel loop just executes. And it looks like how you would like to write this code. So diving in a bit more on how this works, suppose we have two nodes. So the node on the right has the piece of data I that we want to actually access. So what we do is we wrap a pointer to that piece of data I in this template called global pointer. And then on the other side, on the left, is another node that wants to actually take a copy of that value. So it wants to dereference this global pointer. So up above at the title there, that's how the software developer expresses these two mechanisms. And then down below in the slide is kind of the mechanics of what's going to actually occur inside the Grappa system. So we'll start off on the top left. So what's going to happen here is that when you dereference that pointer, it's going to initiate a message to the node that actually contains the actual data, and then it's going to block and wait. So what's going on there is it's context switching to another thread to do useful work. Once enough messages have been collected to that node, eventually some software routine is executed to dispatch those messages in mass to that remote node. That's the dispatch messages blocked there. Then on the remote node, so at this point, the actual physical transmission on the InfiniBand network has occurred. The packet is received. All the messages in that packet are deaggregated. And in this case, it receives the message that says, I would like a copy of I. So the piece of code running there collects a copy of I, creates a response message, places it in the message buffer for heading it back to the requesting node. And then eventually, the network layer picks up that response message, dispatches an InfiniBand message to the requester. That gets back a copy of I, and then it's copied back into J, and then we signal the thread saying, okay, now you can continue your execution. So one thing you might note about this is that we've made the actual request of the data to I, the dereference of this pointer, quite long. Okay, so we've taken what was still a long operation, and we've made it even longer. But as a consequence, we're trading latency for bandwidth. We're able to sort of context switch and stack on much more useful work in the in-between time and keep our processors and our network busy. And we make this trade-off throughout the Grappa system. We're always trading latency for bandwidth, and we're always choosing bandwidth of execution and transmission over latency of individual task execution. Grappa also has the concept of in-memory computation. So supercomputers tend to have this feature as well. You can go to the memory system and say, I would like you to fetch and add this particular piece of data. Or I would like you to fetch and lock it, for example. So you can do the same thing in software, of course. And Grappa has the same concept. So on the right, we have, again, the node that actually contains the piece of data. And on the left, we have is a node that wants to dispatch an in-memory operation to increment that particular piece of data. So things start out pretty similarly. We send a message to the remote node, we block, and then on a remote node, what we do is we figure out that it's not actually give me a copy of that data, it is instead execute this small piece of code that increments it. Now, one of the important things about Grappa is that this is all done in software. So unlike a hardware system, if you want to have more complex in-memory computations, it's pretty easy to do that as well. So if you were to write software in Grappa, what do you need to be aware of in order to write good software? So Grappa requires that you as a software developer express to us lots and lots of parallelism. we're going to use that parallelism to keep all of our resources busy, all of the physical cores in the system, all of the network. And you have to express to us a lot more parallelism than the actual physical resources that are available. So as I mentioned, you want to be able to express to us, even in a system with a few hundreds of cores, you want to express to us billions of threads. So the more threads you can give us, the more we can keep those resources busy, because we're always going to trade off, again, bandwidth for latency. It turns out that data distribution is equivalent to work distribution in this sort of system. So Carlos mentioned that you don't want to have imbalance in your data distribution because that leads to hotspots on particular nodes. The same thing happens in a Grappa system. So the more that you can scatter data around, the more the actual work will be distributed evenly, and the more that things will be balanced. What's also interesting about this system is that if locality exists, you can exploit it. So if locality doesn't exist, what you do is you go off and you fetch this piece of data and you context switch to another thread to do useful work. But if locality does exist, like in a typical map-reduce computation, well, you don't have to do that, right? So it's this interesting system where when locality doesn't exist, you can deal with it, and when locality exists, you get to exploit it. Okay, so some examples. This is the research team, and their professors are giving them a good example about how to drink beer. So here's the top-down breadth-first search algorithm, as I mentioned before, and I'm going to walk you through the various key parts of this. So this first construct, execute on all, this is just a way of saying on every single processor core in the system, I would like you to do the following piece of code. This next loop looks fairly conventional, right? This is just a for loop that's saying, for everything that's in the current frontier of my breadth-first search algorithm, I would like you to go off and do the following loop. And then what it does is it actually spawns a task. This is the enqueue task on, at the particular location of the data, which is the graph node. And that task goes through and looks at the edge list and then processes it, and then dispatches an in-memory computation to go ahead and update the frontier if required for the breadth-first search algorithm. This is obviously the top-down version. The corresponding bottom-up one looks similarly. Again, my point to you isn't that you read this code in detail. My point to you is that this code looks like you would like to imagine the sequential version looks. Obviously, there's some subtleties here to make it work efficiently at scale and in parallel, but it looks largely sequential, which is kind of appealing. Now, how do we do? Let's return to the data. So this is the MTGL graph at scale 25. And I've compared Grappa and GraphLab and a custom Cray MTA machine from prior published results. Now, first of all, what you see is GraphLab is pretty awesome, right? So GraphLab is able to beat custom hardware as well. And Grappa, which gives you this sort of flexible programming model for irregular computations, with simply 12 nodes of commodity hardware can outdo a full custom supercomputer on this computation. And this computation is actually pretty significant. This is the one that really made that supercomputer popular. All right, so if you remember one thing from my talk today, I hope you remember that there is this fundamental trade-off in both hardware and software between latency and bandwidth. And this applies to both computation and communication. And that what you can do in software or hardware is you can always try and get improved bandwidth of execution and communication by tolerating ever more latency. Or the reverse, which is that you can tolerate latency by context switching to another resource and continuing to achieve your bandwidth. Some closing thoughts. Friends don't let friends buy supercomputers anymore. You should buy a cluster of hardware, pour some Grappa on that. You can exploit both parallelism and locality. And Grappa isn't just about graphs, although that's really been our main focus for the last 3 years. It's about any sort of irregular computation. So there isn't much restrictions in the programming model. It's just a lot of fine-grained threads that you have to give us. And we see GraphLab really as an application for Grappa. So GraphLab has lots of many very interesting and useful high-level toolkits that we could port over to Grappa as needed. And the same with MapReduce. So if, you can imagine building in-memory MapReduce computations on top of this framework. My ask of you, we are spinning out a company, as everyone is these days. We are looking for strategic partners. So if you have some problem that you think this technology could solve, We would love to work with you. Go ahead and find us. I'll be around here all day. And I also would love to hear from you over email. Again, we're looking for people that have really big, challenging problems that this sort of technology could be helpful for. And many thanks to the actual people who did all the work listed here. I think I have time for a couple of questions. You'll have to shout. I don't think there's microphones. Yeah.
To get the overall performance of throughput. So in this case, why don't you consider GPUs? Because we have so many cores and it's very affordable.
We are absolutely considering GPUs. Yeah, great suggestion.
A second question, quick question. So you talk about the load bands a little bit, but do you have any specific, particular, schedulers in your system?
Now, scheduling is important. It's one of those areas we haven't invested a lot of effort in so far, but it is definitely an important question to deal with, yeah. No more questions? All right, so it turns out I'm both the moderator of this session and a speaker in it, so I get the pleasure of introducing the next speaker. The next speaker is Chris Ray. A little story about Chris. Chris was in my 2004 computer architecture class. Obviously, he passed. He spent many years as an assistant professor at the University of Wisconsin, and now is a newly minted Stanford professor for the last 10 hours, I believe. So. And despite your furrow, I'm holding the time on you.
Oh, thank you. All right, so thank you very much for inviting me. It's really great to be around a lot of people who are interested in data and GraphLab, and it's really outstanding that there's so many attendees here, so this is great. What I'm going to talk about, rather than giving really a technical talk about what I've been up to for the last couple of years, is give you kind of a strange and crazy talk about things that worry me and challenges that we're trying to address in our own research. And I should warn you ahead of time, it's kind of a strange talk. So with that, what you see on the screen here is some work by one of my favorite artists. This is a street artist from the UK named Banksy. Over the last 15 years, Banksy has become not only a great street or graffiti artist, but he's also gone on to become a very mainstream artist as well. So one of his pieces, I mean, you see he's really technically quite good. That's a graffiti where he's painted two kids standing on each other and they themselves are doing graffiti. He has great work. You should check it out. Now, one of his pieces that I want to call your attention to is this piece right here. Now, if you remember, there's an Andy Warhol of Marilyn Monroe, and in fact, Banksy updated that with Kate Moss in this picture here. And very recently, I think it sold at auction for around £200,000. So it's a very popular mainstream piece now, and Banksy has firmly crossed over. Unfortunately, this whole talk isn't about him. It's great stuff. You should check it out. And for this, I'm going to introduce a second character that we need to talk about. And that's our friend, Mr. Brainwash. So I don't know how many of you have seen the movie Exit Through the Gift Shop. If you haven't seen it, very strongly advise that you see it. It's on Netflix. Great movie. Okay? Without ruining the plot of that documentary or whatever it is, I will tell you that Mr. Brainwash decides over time, after following Banksy around, that he also wants to make street art. And he rips off essentially a bunch of the great street artists of the day, Banksy, Shepard Fairey, and so on. And he's talented. He does some interesting stuff, as I'll show you in a second. But he's not quite at Banksy's level. So here's some stuff that Mr. Brainwash did. You see right there that's the same motif applied to the 2008 US presidential candidates. That's Obama, Biden, McCain, and Palin. And it looks kind of reminiscent of what you saw in the Kate Moss thing we just saw 2 minutes ago. But Mr. Brainwash, not to be outdone, he extended it a little bit, and he started stamping it out. He started doing, Michael Jackson, Condi Rice, there's Leonard Nimoy, that's Larry King, and again, Barack Obama. Why not? He needs his portrait too. So you may look at this and think that, Mr. Brainwash, how successful could he really be if he's just going out and stamping out a bunch of things that Banksy kind of already did and updated? Well, he actually got himself a Madonna album cover. That's the Madonna album cover for her greatest hits album called Celebration. And recently, I think he sold something like 1 million pounds of art. So whether or not you think he's sort of derivative, the man's got a following. So at this point, I hope you're wondering, why in God's name is this guy talking about street art? I didn't think he was serious at the beginning. But yeah, I'll tell you why. Really, I'm making a pretty thin analogy. So the analogy is that today's analytics systems really require artists. They require people like Banksy who know not only sort of the application in detail, the domain science in detail, not only the machine learning in detail, the optimization, the how we're going to solve it, the hardware and how to scale it, the math for how it's actually converging and what's going on underneath. You need people that need to know this entire stack really to get today's systems to work. And sort of in the spirit of what Carlos was talking about as stage 3 of GraphLab, the problem is that there are just too few of those artists that are around. And in any one given project, we'll be closer to someone who's like Mr. Brainwash and less like someone like Banksy. Okay? So what I'm going to argue today is that to take the next leap in building these analytic systems, and what my group has been thinking about for a little while, we need to build tools for Mr. Brainwashes of the world, not Banksy. And you can see a CIDR 13 paper that describes some of this hallucination in a little bit more detail than I'm going to go into today. All right. So a more refined version of this thesis is what my group has been working on over the last couple of months or couple of years, is really this idea that the next breakthrough in data analysis is not scaling new algorithms. And this is really a testament to projects like GraphLab and a bunch of others that have gone on in the research community that have taken data processing algorithms and machine learning algorithms and scaled them up to really what were unimaginable heights even a few years ago. But what I think is going to be the next major breakthrough in these types of algorithms is accelerating model building, even with simple existing models. And the reason I say even simple models, and what I'm going to talk about in the technical portion of the talk, or sort of give you examples for, is that even models that you've known forever, logistic regression, SVDs, things that have been around for decades, actually applying them in practice, as we've heard again a couple times today, is a real challenge. Okay? Even the simple existing stuff that's there. So we don't really need the art necessarily on the machine learning side to really build and impact some serious real-world systems. And I'm going to talk a little bit about this challenge. This is all focused around building this challenge of an analyst accelerator. Okay. All right, so here's our talk agenda. So first, I'm going to suggest to you that that thing I said about simple stuff working well is actually plausible, and I'm going to cherry pick some examples from my research and show you some things that we built that are deployed and people are using, where very, very simple tools allowed us to make improvements on sort of world-class systems. I'm going to contend that even though the final solution that we got to in all of these applications was very simple, actually the process of getting there was the hard part. And that's what I mean by picking the right simple stuff is hard. And what I'm going to do is walk through one case study of a project I'll show you in the first part and show you what are the kind of problems that we ran into there and what are the ways out that we see for building these systems. And then finally, if we have time, I'm an academic, I fully and freely admit it. No startup pitch at the end, sorry Mark. but what I may talk about instead of a startup is talking a little bit about joins. And so, that classic database thing, I may berate you with some theory for maybe just one slide, but only if I'm really feeling mean. Okay, so on to the first part, suggesting that simple stuff may work well. And I'm going to tell you about two projects here. The first project is called IceCube. IceCube is a neutrino telescope that's based at the South Pole. It's about a $400 million NSF collaboration that's been going on for about 20 years. Then I'm going to tell you about this thing called GeoDeepDive, which is basically reading the literature to find out things about energy and so on. Okay? So again, the message of this section hopefully will be clear. Simple stuff is going to work really well in IceCube. Simple stuff is going to work really well in GeoDeepDive, but picking that right simple stuff is the thing that was challenging for us in all of these different applications. So this is a picture of IceCube. That is actually in Antarctica. It's on the South Pole. They've been down there for about 2 decades now, or maybe 15 years. There's actually, you can see there's a runway. They fly in. You have to go through a psych evaluation if you want to stay there over the winter. It's an interesting place. Apparently a few professors have actually gone down there, and then they come in very proud and fancy, and they say, that's great, go move those crates, otherwise we're going to die. So I won't be going down there anytime soon. Anyway, the reason these people are all down there is that they're babysitting this thing. Okay? This is the IceCube detector. So this is a schematic representation. You see that it's basically a gigaton of ice. It's about 2,800 meters, you see, from the ice surface all the way down. And what they've done over the last decade and a half is really drill in through this, these long tubes, these strings or strands they're called. And along those strings, what they've placed are these things, these digital optical modules. These things are about this big around. They're basically light sensors. Okay. Now, when you look at them, that's not upside down. You see that the opening is at the bottom. And if you wonder, why did these guys build this light, this light detectors out there, and they're facing at the rock? Don't they know? I mean, aren't they physicists? Don't they know that light's coming from the sun? Well, they're not stupid. What they're actually doing is using the Earth as a gigantic filter. Okay, so they're not worried about rays that are coming out of the sun. They're worried about those particles that are strong enough to pass through the Earth without interacting with its core, neutrinos. Get into the ice, shoot off light, and from the light that they actually get shot off, they're going to try and deduce properties, physical properties of the neutrinos that they want to study. And I should give them a little plug because they've been extremely nice to us. They have some great papers that have just been released from embargo that are on Science and a couple that are on Archive describing some of the neutrinos they found, extrasolar neutrinos. Very, very cool stuff. I don't understand it at all, and nor should I have to because I'm Mr. Brainwash in this example. Okay, all right. So to understand what we did with them, you have to kind of look at the workflow of how IceCube goes about its daily task. Okay. So what happens is they have all this hardware at the South Pole, and in the ice, about 3,000 times a second, a detection occurs. Okay. The whole thing lights up. And then what happens is they have to decide, is this event interesting? Is it just some noise that's come in because the sun is shining through the ice, or is it one of these particles, these very rare particles we care about? The reason they have to make that decision is because they got to ship all the interesting readings over a satellite link. The rest of the readings are actually written out to tape, and they can only be picked up after winter overs and on sporadic flights. So they would really, for all kinds of research purposes, like to get their hands on that data as soon as possible. Okay. Then once it gets to Madison, Wisconsin, that's where the project is headquartered, they do a whole bunch of more analysis. Now my group actually worked in data analysis in 2 places, both the Madison and some stuff at the pole. And what I'm going to tell you about is what happened at the pole. Okay, so some of the work that we did at the pole where the simple stuff worked well, and then I'll just briefly allude to some of the stuff we've done in Madison, which is a little bit more recent. Okay. So hopefully this video shows up, but you'll see in a little while from the right-hand side of the image, a red line will begin streaking in. This is a particle coming into the detector. When it gets to the detector, light is going to, basically the photons, it's going to emit photons, and those are going to hit the little pieces of the detector, and the lights that are there are those little DOMs, those digital optical modules, one of those 5,000 lights, basically saying, I've got a photon. Now these DOMs are very, very sensitive, so even if you turn them on, there could just be light photons just sort of scattering around, and they'll bounce into another DOM, and so a hit is recorded. So it's actually fairly noisy, and this is a very clean simulation. They don't always look this easy. Now, the data we get back looks like these little light bursts here, and we want to reconstruct that red line. So we can at a first glance tell, is this something that came up through the Earth and is one of the particles we care about, or is it something that was just some solar particle that we don't really care all that much about? Right? So they wanted to recover the track, and what they did over a course of essentially 10 years were build these models that were very physically detailed. So they, for example, modeled all the dust that was in the ice. We actually helped a little bit with that. They modeled all kinds of cool stuff that was going on about the near and the far field effects of light, all kinds of interesting stuff about how the physics of these particles behaved. So sitting down with collaborators, including Ben Recht and my student, Mark Wellens, we started looking at this problem and saying, well, could some sort of simple ideas, these simple ideas really make inroads here in science? Now, what we ended up coming up with was an extremely, extremely simple filter, okay? Extremely simple regressor. It was basically, if you care, 2 Huber loss regressors stuck together. These are things that have been around forever. It's just L2, L1 kinds of regressors, as simple as it gets. Basically concatenated together with little filters in between, okay? The final code was, you could have written it in a student meeting. You could sit down there. Actually, I did actually write some of the ADMM that is used to solve it in a student meeting. Very, very simple stuff. But even that allowed us, over the state-of-the-art models, to get 10% fewer false negatives and about 1% more neutrinos. Now this work is actually hopefully being presented in Rio next week, if Mark can make it to Rio with all the riots and everything, but hopefully he gets it, okay? But these guys that we worked with, these IceCube people, were awesome. Not only did they decide that these simple models were great and they would let us write a paper about it and put their IceCube stamp of approval, they actually put it in the detector. And so for about the last little over a year and a half, I think, they've been running, Mark's code has been running on the pole. And it's been running every day on 3,000 events per second or 250 million events per day. This very simple, robust model. Okay? Now in the end, if you looked at the code, it's not impressive. It could all fit in like one nice Emacs buffer on a nice 3-monitor setup. You would have more than enough space to look at the code and check your mail. It's very, very small. But the hard part was figuring out which of those filters to put in and in which order. Okay? And so that's what I mean by saying picking the right models was difficult. Okay? All right. So this same story actually played out. It's not a one-off event. We applied exactly the same sort of methodology, this sort of intense data debugging with relatively simple algorithms. And this actually spawned a little bit of theory that we're still trying to hammer out the details about. But for this problem of detecting whether or not two events are coincident in the detector, we actually have a solution that has 98% accuracy, which is actually over the about 90% accuracy of the previous solution. So it's a big improvement. Okay. And I should say all of these things are up on our YouTube channel if you want to watch videos that are produced by my students, so you can watch and check them out. Okay. So in both problems, and actually everything we've done with the IceCube team, the algorithms have always been simple. The final code has been trivial, usually. It's something that if you look at, you're sort of embarrassed that this is a scientific computer science contribution, but it was finding that right code that was actually complex, sitting down, doing the data debugging, and figuring it out. And also, as I should say, we expressly didn't do complicated algorithms. Huber loss, L2L1 regression, that was as, least squares. That's as difficult as we got. Okay. All right. So you may think, okay, this is a pretty specialized physics problem. Maybe if you think physics is simple and, it's kind of just some particles banging around, who really cares about it? I like it, but whatever. So what I'm going to do is show you something that I think is actually much more difficult, in that it has to deal with reading text, so human text. And what I'm going to do is I'm going to show you a little video for about 2 minutes. Let me plug this in. Should have done this earlier. We did a sound check. We'll see if it works. It's always exciting. And I'm going to play you this little video.
Geo Deep Dive is a collaboration between Shannon Peters Geoscience
It's about 2 minutes
Group,
long, so the intro's a little long, sorry.
Research Group, the Center for High Throughput Computing, and the Hazy Research Group. The goal is to help geoscientists extract data that is buried in the text, tables, and figures of journal articles and websites, sometimes called dark data. To bring dark data to light, we use the Hazy Research Group's machine reading system. The Geo Deep Dive system extends a database created by Professor Peters' group called MacroStrat. MacroStrat contains information about rock formations and individual geographical units. Here is an example, the Barnett Formation. The Barnett Formation contains several units that are spatially distributed as shown on the map. It is also temporally distributed over several geological time intervals. MacroStrat contains over 36,000 rock formation units like these. There is also geologically relevant information in journal articles like this one. As we'll see, Geo Deep Dive extracts information about these rock formations from journal articles. As of today, Geo Deep Dive has processed over 36,000 research papers. This is the Geo Deep Dive homepage. It shows a summary of the results of Geo Deep Dive's deep linguistic and statistical processing. Geo Deep Dive is still in its initial stages, but we are excited about the amount of dark data that we have already uncovered. For example, we found about 500,000 mentions of formation units from 36,000 documents and about 24,000 measurements of the units. Our preliminary analysis leads us to believe that there is even more dark data out there. We are currently working hard to uncover dark data and integrate them into Geo Deep Dive.
So that video is a little bit out of date, and it does a pretty good job at describing sort of what the Geo Deep Dive project is doing, but it doesn't tell you why we're really doing it. So the reason we're doing this is if you think about today how geologists work, by and large they're only able to visit a small handful of rock formations that they're interested in. They're able to only read a small handful of papers about the relevant phenomenon they're interested in. And so as a result they have a very microscopic view of North America or whatever phenomenon they're studying. And the idea is to read papers, and now at this point we've read not just 36,000 papers, but close to 1 million papers in this area, to put together not just journal articles, but also all kinds of information that's in government reports, the USGS, and so on. All right. Now once we build such a database, we can start to ask already interesting questions. So we can ask things, for example, like how much carbon is in North America? Now that may seem to be question that you think we would have a good handle on, but if you, for example, read the Atlantic Monthly in May, you saw the cover article was, what if we never run out of oil? And the reason that those estimates of how much oil or natural gas we have keep going up is we have no idea what's in the ground. And so the hope is that by being able to simply assemble what's out there already in the literature, we can get this stronger macro view. We also eventually want to do things that require inference. So not just collecting a data set and answering questions over it, but actually being able to go one step beyond that and infer which elements of shale, for example, are recoverable. Right now, this takes a PhD to come in and look at all of the various factors, porosity, water tables, all that interesting stuff, and put it together. Okay. Now, to understand why this is hard or difficult or complicated, the problem is that we need to do these extractions with extremely high precision, and it turns out also with really high recall. So the accuracy with which we extract facts has to be very, very high for people to do science. And in contrast to a lot of the work that people have been doing over the last couple decades in NLP, the sort of state-of-the-art of what people are able to do on these open benchmarks, which we contributed to as well, are in the 40s. Okay? So we had a lot of work basically when we started this project to move beyond to get this high level, high quality that we were after. And the key, and we've been able to actually do this in some domains, the key to doing it is really three things. The first is we have really smart geologists that we work with. They're able to tell us, these are the things that are relevant. And I'm going to dive into this in more detail in a couple minutes. We also have very, very simple models. In fact, the models that are used to construct this are no more complicated than logistic regression. Right? The other bit is that we do a very serious process of feature engineering, and that's what I'm going to spend the sort of technical portion of the talk describing. Right? Before I do that, I just want to give you a sense of actually what goes on in any of these systems and how it looks like to actually run one. So the first bit of this is what the deep dive framework looks like, which is powered by GeoDeepDive. The data acquisition phase, we read a couple million documents. Right now, about 122,000 of them are what we call curated. This means that someone has either recommended we look at the document or a geoscientist has flagged it as an interesting journal. We then run all kinds of NLP on top of those documents, basically every toolkit we can get our hands on. And these are all publicly available toolkits, and so is the data. This takes around 4 million CPU hours to run this, so about 450 CPU years to be able to run over all the different terabytes of text and extract all that meaning. Okay? Once we do that, we actually put everything onto one particular system. It's actually one just beefy high-end server, which was called Felix a while back. That's why there's a cat juggling mice. And then we put it up to that web front end that's there. Okay? Now for us, when we actually build such a system end to end, you notice that most of the time, most of the processing really goes into that first initial stage, the high throughput stage of running all of the NLP. And actually the statistical part that we're running, which is basically Gibbs sampling and some simple logistic regressors, that takes almost none of the time in the pipeline. Okay? All right. So just to plug a little bit about scaling stuff, I should also mention all the data that we produce in this project, since we're academics, is all free. There's a website where you can download all of it. We have to ship you hard drives, but we've annotated all the clue web crawls, common crawls, all these articles will be free, modulo some weird publisher issue that just came up. But that's neither here nor there. So the stuff that we do here is all stuff that you can get. The feature construction is all SQL and high throughput. Condor is free and open source. Greenplum has a community edition. It's all just standard SQL. We have our own little nerd ways we like to do, factor graph sampling and weight learning. And you can definitely go check out our papers of, lock-free this and, scalable that, whatever. But that doesn't matter anymore because things like GraphLab are out and you can just download GraphLab. And GraphLab has pGibbs, which basically does a lot of the factor graph inferencing for you. And it also has very similar things that only differ in the most esoteric nerd details from the hog wild stuff that we do. So I contend with all this great technology that's out there, the challenge is really not scaling anymore. We've built this system. We were an extremely small lab in Wisconsin. I think 2 graduate students built that entire infrastructure end to end and got the first demos working. The challenge was really figuring out how do you get the right features? How do you figure out what are the signals that are sort of indicative of all the stuff you're interested in? The rest of the scaling, for us, was not a problem. Okay? And I should mention also, we run on a web crawls and all that other stuff. There's a demo called Deep Dive you can check out. So if that's not the problem, then the message really here is that helping Mr. Brainwash, and this example me, I know nothing about geology, be able to quickly build the right model. Okay? And often, very often with technology like GraphLab, the coefficients are learned in the blink of an eye. Okay? All right, so now let me dive in a little bit more to being able to, what I mean by picking the right simple stuff is hard, and sort of dissect that GeoDeepDive case study in a little bit more detail. So first, to motivate what I mean by feature engineering, there's a great paper that I want to plug. It's called The Unreasonable Effectiveness of Data. If you haven't read it, I'd kind of be shocked. If you haven't, you definitely should. It was by Alon Halevi, Fernando Pereira out of Google. And basically, they have this great line in there where they describe this phenomenon that they saw again and again, and we saw in our lab again and again, which is that a simple model, given enough features and given enough data, almost always beats a complex model. And so the natural lesson to take away from this is that you should engineer getting the right signals into your model, not advocating more complex models. So seeing this, what we decided to do was then go and watch the way that people were building models. And so we actually poked around in an insurance company that was nice enough, actuaries, and started to watch real people build models, both in my lab and in other places. And we observed something that looks like marketing BS, but it's not. I think there's actually content here, but maybe I'm just deluding myself. It's in a paper, so what can you say? It's called the E3 cycle, okay? And the idea is that whenever anyone gets data, they go through this cycle again and again and again, and that systems don't really help them go through this cycle today. So when they get the data, the first thing anyone does is they explore it. They figure out what's in it, what types are in it, what people are in it, all kinds of grunt work stuff. Then they extract information from it. They write a bunch of features. And then finally they evaluate it. And if you look at where their time goes in this process, a lot of their time does not go into learning the coefficients, for example. It really goes into the rest of this cycle, right? Learning the coefficients of a model is actually just one link in this much, much larger chain. Okay? So the question is, can we do anything to help support them in this grunt work data munging, extracting features from data, and also evaluation? And I do want to also say evaluation is actually where we spend in my group most of our time. The rest of even the grunt work data munging, we feel like we have down a little bit. But actually evaluating and understanding why and where your system misbehaves is where almost 90% of my graduate students' time goes. Okay? So let me dive into each one of these a little bit more. So the first one is this grunt work statistics. When we first started, we had about 20,000 papers that we had downloaded and gotten the rights to. We had a dictionary of different places that we were interested in. And we had a variety of these geological reports. These were things in databases, files, key value stores, XML. And we didn't know a whole host of things. We didn't know the file formats that we were dealing with. We didn't know the fields that were in the tables. We didn't even know the distribution of tables that were out there. But it turned out that even though this was a very classically hard data integration problem, machine learning allowed us to deal with almost all of this. And it was kind of magical for me at first, and I thought I had been deluding myself. But really what it turned out is that the machine learning tools that we were using essentially allowed us to cope with much, much lower levels of structure than we were used to as traditional database people. So we treated basically everything that we would see as some kind of observation and used that to predict what we were actually interested in and stopped worrying about whether or not we were perfectly matching or aligning all of our schemas. And I don't have a very crisp way to articulate this, but that sort of let it work for itself idea and just give it all signal really was an eye-opener and allowed us to build this system end-to-end very, very quickly. Actually, we got the first demo up and running in about I think it was 6 weeks, 2 weeks to the first very initial thing and 6 weeks end-to-end. The second challenge that we faced in these kinds of tasks are what we call unknowable specifications. And what I mean by this is as a Mr. Brainwash writing these, you have no idea what you're actually doing when you begin your project. And so what you usually do, or what we do in our lab, is we just start writing. We just start building stuff. And then we go and show it to whoever is actually the expert in the area. And when we would show it to our experts in this case, who are the geologists, they would tell us all kinds of stupid mistakes we were making. Like we would match formations incorrectly. And they would tell us, well, after a formation name is used for the first time, it's shortened. And that's the way it is, and you can bank on that rule. That's something you should bake into the system. They would tell us all kinds of other things. We were building this very high-quality carbon map. And we were looking for every time, total organic carbon measurements were actually expressed in the literature. And they were expressed very infrequently. But instead, black shale indicates that there's carbon present. And so by knowing that there was a mapping from finding incidents of black shale in the literature associated with a formation, that we could actually predict how much carbon was in there, was really eye-opening to us. And we would have never known that on our own. Now, the point of all this is that CS people didn't know this, could not be expected to know this, and no developer in their right mind would know the intricacies of how geology works unless you happen to find one of those true artists who knew all the way, sort of from geology all the way down to hardware, how to make this thing work. That simply doesn't exist. So what we learned is that we had to be comfortable with our specifications constantly being refined, and we started to try and work at developing these easier end-to-end pipelines. And we don't have a solution for it, but we at least are aware of the problem, and I think that's one of the stages. The last bit of what we talked about is unexpected failure. And when building these systems, the first lesson we learned is that anything that we thought was a good idea would not work, and anything we thought was a stupid idea would. So this seems to be a very good way for me to judge. I just say the opposite of whatever I think when my students come in, and they seem to be doing much better for it. So that says something about me, but either way. So we had this problem where we had to basically extract locations and figure out actually where on the map are they talking about. And it's a detailed problem that has all kinds of interesting and painful problems to it. Okay? So one developer decided they were going to add in all kinds of sophisticated natural language processing techniques and tools and build new models, and they didn't do any error analysis ahead of time to support this. And this was a painful lesson because after about 2 weeks, we realized that we were actually performing worse than the baseline, not better. And that was actually something that we learned right away, which is to make all of these systems as simple as possible and, most importantly, as easy to evaluate as possible. Okay? So the desiderata of these systems, we don't have them yet. This is just like the vision of what we want to build and what we're trying to, is that these systems should learn from analysis, both to automate routine tasks and to avoid repeated failures. I think it's interesting to not consider machine learning as just one task done by one person, but to consider it as a long pipeline or sort of cycle of tasks done by many, many people, and there's a huge opportunity to learn from all of that and collaborate around how to build these models. And so we've come up with some technical stuff, and there's some nerd stuff about how this actually works. That's a lot of fun, but I won't bore you with because I'm short on time. Okay, so with that, what I want to do, rather than, see, I was going to hammer you with joins. It would have been fun for you. Anyway. So no more joins. I do want to plug Logic Blocks is talking later. Awesome company. They have this great algorithm called the Leapfrog Tree Join, and they engage with us quite a bit. They're awesome people, so I'll let Moham talk about that. So in conclusion, all I want to say is that what we've really been doing here is talking about how to make, and this is a challenge that's come up several times already today, how to make simple models widely usable and available by non-artists, like Mr. Brainwash. And the Analyst Accelerator may be one way to take that next leap. So before I really conclude, I want to show you this. Our code and data is available on that website. Street Art Utopia is great. They have all your favorites. If you want to go look there, these images are from that. Toubon is not safe for work, so don't open it at work. Thank you so much.